Welcome to this talk. My name is Zeyuan, a PhD student of Professor Simon Guest at Cambridge. Now I'm waiting for Viva. Today I want to introduce the local rigidity analysis of rigid origami. Rigid origami has shown its wonderful potential as a foldable mechanism, and we have seen many results focusing on the kinematics and mechanical properties of foldable rigid origami. Here I will consider a different viewpoint, a rigid origami that is not foldable, and it turns out that there is a hierarchical relation of different levels of rigidity. In other words, for rigid papers, how close it is to foldable, or the stiffness are different. Considering the different levels of rigidity for rigid origami might give a novel perspective for the development of new folding patterns, or for the design of origami structures where some rigidity is required. The levels of local rigidity that we will discuss here are first order or static rigidity, pre-stress stability, and second order rigidity. The first order rigidity is equivalent to static rigidity, which implies pre-stress stability, which implies second order rigidity, which implies rigidity, but none of this relation is reversible. Next, I will introduce them one by one with examples. This hierarchical relation is basically the same as classic rigidity theory on bar joint framework, but there are some special features for rigid origami. I will talk about this at the end. All the local rigidity concepts developed here are based on the folding angle expression. The rigidity matrix dA over dρ is obtained from the first order derivative of constraint on the folding angles. A first order flux is a vector in the null space of the rigidity matrix. We further claim that the form of load is a set of equal and opposite torques applied to the panels on each side of each inner crease, and the internal force in equilibrium with external load is in the form of omega times dA over dρ equals to L. A self-stress is a vector in the left null space of the rigidity matrix. A rigid origami is first order rigid if the null space of rigidity matrix is 0. A rigid origami is statically rigid if the column space of the rigidity matrix is 4 rank. Therefore, they are equivalent. The example shown left is a degree 3 vertex, which are both first order rigid and statically rigid. This form is a comparison between rigid origami and bar joint framework. In the folding angle expression of rigid origami, a body is an inner crease, and the magnitude of folding angle represents the configuration of a rigid origami. The linkage among bodies is the consistency around each vertex or hole. The form of internal force of rigid origami is a torque inside each inner vertex, and a torque and a force inside each hole. Now we move to the pre-stress stability. We will describe an energy function U that gives the potential energy stored in the paper. We require U to have continuous second order derivative, which is further required to be positive definite from the positive stiffness of a material. We could derive the total stiffness to second order in this form, and a sufficient condition for the rigid origami to be stable is the stiffness being positive definite. It turns out that a rigid origami is pre-stress stable if and only if the stress matrix is positive definite, restricted on the collection of first order flux. The two examples shown left are both pre-stress stable. Next, we will discuss second order rigidity. A second order flux is a pair satisfying this equation when rho prime is a first order flux. We could also apply stress test to second-order rigidity. The result is a rigid origami is second-order rigid if there is a suitable self-stress for every first-order flex such that the quadratic form is greater than 0, while pre-stress stability requires a uniform self-stress. The example shown left is rigid but not second-order rigid. Last, I want to mention some special features of rigid origami compared to the classic theory on bar-joint frameworks. First, in the folding angle expression, the only trivial first-order flex is 0. Second, the constraint on folding angles is essentially a high-order polynomial system, while for bar-joint framework, the constraint is quadratic. Third, the effect of self-intersection could not be revealed from the algebraic analysis. The collision between panels might also induce rigidity. Fourth, consider the example shown here. The two folding angles are minus pi, but the configurations are different. Different stacking sequence might also behave differently when considering the self-intersection of panels. Fifth, when some folding angles are plus or minus pi, a flex is only valid when it points away from plus or minus pi. An example is shown at the right. Such rigidity also cannot be predicted by the local rigidity analysis.